Thank you very much for listening to my presentation today. Today, I'm going to talk about a simulation framework that is about a paradigm on how we organize our simulation software that is effective for modeling the dynamics of generally articulated spacecraft. Now, what do we mean with generally articulated spacecraft? Well, in astrodynamics, we like to think of our systems as point masses or rigid bodies with position and maybe attitude. In reality, most systems are more complex than that. They're composed of several elements that move with respect to one another. For example, a satellite can have solar panels that deploy and rotate to face the sun. It can have reaction wheels that they obviously rotate, and if they're unbalanced, they change the inertia of our system. And we have even more obvious examples, such as space stations or robotic arms. So when I speak of generally articulated spacecraft, I really mean any spacecraft that has multiple elements that move with respect to one another. And in the world of robotics, we call these systems multi-body systems. The problem of modeling the equations of motion of these systems is that as the spacecraft complexity grows, so does the modeling and simulation complexity. Now, for a point mass or a rigid body, I'm confident that everybody that's listening to this recording can come up with the relevant equations of motion. However, when we start having multiple bodies in a spacecraft, things start getting trickier. Now, at the AVS lab, some of my very smart colleagues have made great strides at coming up with techniques to efficiently define the equations of motion for spacecraft that have basically a main hub and then components attached to it, like solar panels or robotic arms. One of such techniques is the back substitution method. Now, this method has significant challenges. Namely, extending the capabilities of this method requires very lengthy analytical derivations. These are just some of the equations from last year's ASC conference on a paper about modeling robotic arms with the back substitution method. Needless to say, this is a pretty lengthy and complicated derivation. Now, as we have even more complex spacecraft, like if they have branching body topologies, methods like the back substitution break down. And as we add even more features like flexible bodies, contact dynamics, modeling and simulation just kind of grows exponentially in complexity. So, given that we do want to model these kinds of generally articulated spacecraft, the question is, how can we create simulation tools that are intuitive and scale nicely with spacecraft complexity? Well, the solution, I believe, lies in forsaking this path of finding analytical solutions for various complex space systems, because it just grows exponentially in complexity, and instead taking a page from the method developed by roboticists and using a multibody dynamics engine that use recursive algorithms such as Featherstone or Keynes algorithm for multibody dynamic systems. Now let's dive a little bit deeper into what multibody dynamics entails. Here we represent the configuration of a spacecraft with the generalized coordinates vector, which contains the position, velocity, attitude, angular velocity of our spacecraft, and also contains the joint angles of our robotic arms, for panel pitch angles, reaction wheel speeds. Now, the time evolution of the spacecraft state is then all about finding what's the time derivative of these generalized coordinates. And in the multibody dynamics approach, we can divide this computation into three phases. The first is the forward kinematics, which is all about given the generalized coordinates of our system, how do we compute these poses and twists of frames of interest? So for example, assume that we know the joint angles of a robotic arm, how can we find the position and the pointing vector of a camera at the end of this arm? Second, it's all about finding the forces acting on our system. And this includes forces acting on the bodies, like atmospheric drag, torques acting on the bodies, like gravity gradients, and forces and torques acting on the joints, such as coming from a motor. And finally, we have the forward dynamics, which is given the current coordinates and given the forces acting on the system, what is the time derivative of the generalized coordinates vector? Now, our argument is that basically these forward kinematics and forward dynamics algorithms, they have tried and true solutions that work for generic setups, and that it's not necessarily of interest for astrodynamicists to understand the details of these algorithms. On the other hand, computing the forces acting on the system, this is very interesting for us because it's basically all about defining the environment under which the robot operates and the control that is acting on it. And so we want to make this task as easy as possible for the developer. Now let's talk about the simulation framework. The simulation framework that we propose is a model-based message passing framework. And what that is basically all about encapsulating computation of our dynamics into their own models, their own self-contained pieces of simulation. We have clear inputs and outputs, which we call messages. Now, power kinematics is a good example of a model because it takes as input the generalized coordinates of the system, Q, and it outputs messages containing the pose and twist of each frame of interest for simulation. Forward dynamics is similarly an interesting model because it takes as inputs all the forces and torques acting on the system, and it outputs the time derivative of the generalized coordinates. Now, what we call dynamic models is what lives in the middle of two, and this is what the users define. Now, these are also self-contained, and they have a very specific task and clear inputs and outputs. The inputs to these models can be information coming from other places in the simulation or outputs of the forward kinematics model. And what it outputs is messages that can either connect to other models or that can basically produce the forces and torques that are acting on the system and they are connected to the forward dynamics model. And so the finer simulation is all about writing these models that are kind of like functions in programming, right? That take some inputs, produce some outputs, and connecting them together. Now, why do we care so much about these models is because they are a method of encapsulation of functionality, which it's all about increasing reusability and maintainability because it's easier to test, it's easy to document, it's easy to understand what these models are doing. Because you don't need to think about the entire context of the simulation, just where are my inputs and where are my outputs. As an example of how such a simulation framework can be applied, let's consider a solar array deployment scenario where each of the panels is actively controlled through a PID controller. Now, of course, the controller's objective is for a panel joint angle to follow a certain smooth deployment profile. To model this, we have two models, which, given the simulation time, they output the desired joint angle and desired joint angular velocity. We also take the current angle and the angular velocity from the forward kinematics model, and we connect this to the PID controller. Of course, if we know the desired angle and we know the current angle, we can compute a torque that should act on the joint so that this desired angle is achieved. Now, there's many more details about this simulation example in our paper, and also the source code is on GitHub. But for now, just focus on that these three models, basically, we can reuse across different simulations and within the same simulation to control each of the joints. And together, they all define the torques acting on the system. The torques are interpreted by the forward dynamics model as a time derivative of the generalized coordinates, and the resulting is what we see here in this video of this smooth simulated deployment. Now, let me wrap up with some conclusions, and that is that we believe that it is effective to think about articulated spacecraft as multi-body systems, what robotics is considered multi-body systems. And that's because through this lens, we can apply many of the well-established algorithms in the literature of robotics for the purposes of astrodynamics and GNC, such as forward kinematics and forward dynamics. We also argue that partitioning our dynamic calculations into models that talk to each other through messages, basically about encapsulating our implementations and defining clear interfaces, this helps with reusability, maintainability, testing, and documentation. And overall, it makes for a nicer to use simulation tool. And with that, I'd like to acknowledge that this research was supported by the Jet Propulsion Laboratory, Caltech, and NASA. And if you have any questions, hopefully the paper solves some of them. I'm also reachable through email. And I hope that I can see you and follow conferences maybe next year at ISE. Thank you very much.